Right. Okay, I think this is where we ended. So I just wanted to, before we get into the details of the intralateral system and take it step by step, I just wanted to follow up on this sort of old terminology. So historically, the left side of this just shows you the normal schematic that we've all seen of these two systems. But there's some historic terminology that you might see somewhere, and that's neo-spinal thalamic versus paleo-spinal thalamic. And so subtly different here, the neo-spinal thalamic is sort of the dogmatic spinal thalamic tracts that we all consider synapsing, ultimately impinging on the VPL thalamus. The paleo-spinal thalamic tract are axons that travel alongside the VPL bound axons, but actually synapse an intralaminar nuclei of the thalamus. And so they transmit different, still nociceptive information, but different, slightly electrophysiologically, you can see by the multisynaptic pathway, and qualitatively different nociceptive information. This pathway is polysynaptic, and so one thought is that it transmits more persistent types of information and might be involved in the establishment and persistence of neuropathic pain that persists beyond the end of the painful stimulus. And so that's a bit of an aside, but just in case you hear the terms neo and paleo spinal thalamic, these are just adjacent projections in that spinal thalamic tract with potentially different nuclei of interest in the thalamus. Okay, so the anterolateral system then, taking the same step-by-step approach we took for the dorsal column medial lemniscus system, what tests on the exam test function of this pathway? So this time you're looking for crude or deep touch, or pin or sharp pain, or sharp touch, or temperature. So the tests of interest then are pinprick typically, and it need not be a sharp pinprick. A pressure, a focal pressure point will test this as well, but it's typically clinically done at the bedside with pinprick, and either hot or cold stimulation, although pinprick is the easiest and most common, just to do something at the bedside. And again, we're taking all the steps through this pathway from the spinal cord all the way up through the brainstem to the thalamus and the cortex. So sensory information enters the spinal cord, here's my dog, via a small diameter primary afferents, and so enters the dorsal horn, and these tend to be either smaller nerve endings, less specialized, or just free nerve endings. Yes, in the skin. And they enter, of course, via the dorsal ganglion, but they enter the superficial dorsal horn and either synapse immediately or ascend or descend 1 or 2 levels prior to synapsing. And the white column that they make in the dorsal spinal cord is, when they ascend or descend a couple of levels, is known as Lissauer's tract. Now, this is really hard to visualize for some people. So this little YouTube video, one of those little drawing sketch videos, helps a lot. In fact, the same artist does videos for all of the tracts, and probably they're all worth watching. But to get Lissauer's tract visualized, try this little video. Here's sort of the schematic representation of Lissauer's tract in your book. The schematic over here and the actual section with a myelin stain over here. And so you can see the pain or temperature afferent enters the dorsal white matter, and this is Lissauer's tract here, this column of white matter that's dorsal to the dorsal horn. And in over here, you can see that the dorsal root is caught in section here, and Lissauer's tract is right here, where the axons of those small or thinly myelinated fibers sometimes travel rostrocaudally for a few segments before synapsing in the dorsal horn. The large fiber entry zone is a little more medial, and you can see the arrows here are perhaps proprioceptors synapsing deeper in the dorsal horn, but the small diameter afferents are going to synapse superficially, and so some of them will synapse here immediately, the majority of them, and then they will interact with a second order sensory neuron that resides in that dorsal horn and gives rise to the spinal thalamic tract by traveling through the anterior commissure. This is a stain, a histological stain of a single spinal thalamic tract neuron, and you can see it happens to reside deeper in the dorsal horn. So this might be representative of this neuron right here, but it has a dendritic tree that travels to the superficial gray matter. So all of these dendrites of this neuron reside up here, perhaps receiving input akin to this one, but a cell body a little deeper. And then it's going to extend its axon to the spinal thalamic tract. So axons of, as I just said, the secondary sensory neurons cross in the anterior commissure of the spinal cord. So this is the decussation point of the spinal thalamic tract. And at this point, it enters the intralateral system. And so it's showing you sort of two options for an A delta fiber and a C fiber here. A delta in blue, thinly myelinated, C fiber in red, unmyelinated. And again, the general pattern is most superficial synapses have second order neurons in the superficial dorsal horn. My goodness, I don't even know if I'm talking language. Let me try again. Dog interrupted. The general pattern here in terms of synapses in the dorsal horn, superficial to deep, is the smaller fibers terminate more superficially, whereas bigger fibers penetrate more deeply. Both cross and enter the intralateral system. The axons of those second order sensory neurons ascend in the anterolateral white matter of the spinal cord. The spinal reticular tract exits at the level of the pons. But remember, it's not a branch from here to here. It's axons traveling all the way from spine to reticular nuclei, or spinal cord, rather, to reticular nuclei. Spinal mesencephalic tracts, as the name suggests, exit in the midbrain. And the spinal thalamic tract projects primarily to the ipsilateral VPL thalamus, and then on to the primary somatosensory cortex. Lindsay would like to participate in this portion of the lecture. Okay, so, I will get into the right mode. Now, so this is that additive schematic again, where nociceptive information from the leg enters the lumbar cord, crosses at the anterior white commissure, and ascends in the anterolateral spinal cord. Information from the arm is added at the cervical thoracic levels, and information from the face enters typically at the level of the pons. This takes a bit of a weird progression for this kind of information, so it descends a bit before joining the spinal thalamic tract, and remembering that it synapses medial in the thalamus to the other information, but it does travel alongside it. So analogous to the dorsal column medial lemniscus system, just something to remember for when we get to the cranial nerves, which carry this information from the face. Now, I know Sam has talked about the nucleus, the nuclei, the thalamus. So, before 426, we sort of consider the thalamus grossly as a nucleus. It's actually a bundle of specialized nuclei. And this includes the VPL, with dealing with sensory information from the body, the VPM, dealing with sensory information from the face, and the intralaminar nuclei that have more integrative and different roles. So I won't belabor that. Most of these nuclei, as Sam has told you, are relay nuclei. They receive inputs from different sensory centers and project to the cortex. The intralaminar nuclei have more diffuse projections. And in fact, there's another category, reticular nuclei, which are involved in alertness and consciousness from the reticular system. Now, when we get to locating lesions in the CNS, and this is really what we've been building to, which we'll do this weekend tutorial, most of us are familiar with the lateral corticospinal tract, and it crosses, of course, at the pyramidal decussation at the junction of the cervical spinal cord and the medulla. We now know that the dorsal column medial meniscus pathway crosses at the internal arcuate fibers of the lower medulla, and the anterolateral pathways cross in the anterior commissure of the spinal cord. So the central point the central thing about locating lesions in the CNS is looking at modality. Is it movement, or two sort of main modalities of sensation, and considering whether the lesion occurred rostral to the decussation for that specific modality or movement, or caudal to the decussation. If you're caudal to the decussation, the symptoms are on the ipsilateral side of the body. And that's really the key to this whole portion of the course. Now, when we get to clinical cases, this slide is just to take us through a bit of clinical terminology, because normally, or quite often at least, loss of sensation is not absolute. So it's not just loss of sensation. You can have abnormal sensation or paresthesia, including pain. And of course, the location of the sensation is important, but also the character of the sensation. So abnormal sensation, like loss of sensation, happens below the level of injury. But if it's damage to the dorsal column medial meniscus pathway, then the abnormal sensation is qualitatively similar to sensation in that pathway. So tingling, numbness, tightness, gloves and stockings, constriction of the hands and feet is characteristic of dorsal column medial meniscus pain. Excuse me while I wrestle a dog. Who doesn't want to grouch? Who wants to stay in? Conversely, if you damage the intralateral system, you can have loss of ability to distinguish pain, but you can also have paresthesia that resembles the information traveling in that system, like sharp, tingling, burning pain. So all of these are examples of paresthesia, which is abnormal sensation. Subtypes of that, a subtype is dysesthesia, which I can barely pronounce right now, is an unpleasant abnormal sensation. So paresthesia, partial loss of sensation or abnormal sensation. Dysesthesia, unpleasant abnormal sensation. So not only is it abnormal, but it's unpleasant. You don't like it. When we get into pain, there are many categorizations of pain, but two words I want you to know are allodynia, which is pain in response to normally innocuous stimuli, and hyperalgesia, which is exaggerated or prolonged pain in response to a normally painful stimulus. So to give you an example of allodynia, some people with neuropathic pain conditions, the presence of clothes on their skin is excruciating. And so that would be an example of allodynia. Or if you stroke a cotton swab over someone's hand and they yell, right? That's allodynia. Hyperalgesia would be if you punch someone in the arm and instead of going, ow, they, oh my God, my arm. That's hyperalgesia, right? So both of those describe pain. Dysesthesia is a bit more general. It's just unpleasant. Can be painful or uncomfortable. And paresthesia is the biggest, most general term, which is any abnormal type of sensation. And so what we're going to get into is a whole bunch of spinal cord syndromes in tutorial that combine both motor and sensory information, and learning how to localize those in clinical cases. And so I'll just get you to save these little schematic diagrams for tutorial. I'll show you how to use them when we get to tutorial on Thursday, and with a combination of my stuff and Sam's stuff for motor and descending motor and sensory, or descending motor and ascending sensory. Yeah, that's what we'll be talking about. I'll see you then.